Okay, so now we're going to discuss what topology can do for you. So what can topology do? Okay, we already briefly talked about this idea that topology can be used as a method for classification. Okay, so it provides a means of characterizing sort of global properties of an object. Okay, there's another important aspect that's tied to sort of topological invariants are that they have a certain measure of robustness. Okay, which is that since topological invariants are by definition insensitive to smooth, it's like transformations. Transformations which are smooth. It's like, and the inverses are smooth, right? So since it is insensitive to sort of deformations of the object, right? Topology provides a method of analyzing objects which is in some sense robust to measurement noise. Okay, there's this interesting aspect. It's like that topological. It's like sort of techniques, if you will. It's like allow you to integrate local information, like it's like connectivity, to then say something global. It's like about the properties of the object. So there's a local to global aspect to it. So topology provides sort of the tools, right, to sort of combine local information or synthesize local information. Right, to yield global information. And then finally, it's like there's this idea of topology as a means of proving that certain things are not possible. So what oftentimes referred to as topological obstructions, right? So obstruction. So often provides a simple way of showing that certain things are just impossible, right? Okay, perhaps sort of, what's one of the most well-known examples of something which can be proven, it's like using topological obstruction techniques, is the Harry-Ball theorem, right? which basically says that you can't comb, it's like, say, a coconut continuously, the hairs of a coconut continuously while having all the hairs lie flat, right? So can't comb sort of hairs of the coconut sort of continuously while having all the hairs lie flat. Okay, sometimes, this sort of phenomena is sometimes referred to as a cowlick. Okay, usually in reference to actual hair. Okay, so anyway, so the upshot, if you will, is that topological techniques provide you a very robust way of classifying objects, particularly if these objects are noisy. Okay, and so that's going to be the main reason from a applications perspective why one might want to use topological methods is because of this robustness to noise. Okay, so simply put, right, in applications, sort of topological methods provide a means of robustly distinguishing sort of between sort of qualitatively different objects in a manner that is insensitive to measurement noise. So that's going to be some of the things we're going to look at. In particular, we're going to look at this idea of persistent homology. And so persistent homology is an attempt to try to extract topological properties out of point cloud data. So imagine you have points which are sampled, it's like from some sort of object, and you're trying to infer, it's like from that point cloud, it's like what the topological properties of that thing are. So the problem, of course, is that when we looked at these examples about the torus, the cylinder, it's like in the sphere, and we're trying to compute the Betti numbers, right? That really relied on knowing sort of connectivity information, so how points are connected to each other. And of course, if the only thing you have are point cloud samples, you don't have that connectivity information. So a big part of this course, it's like, will be in this area known as persistent homology, which tries to take that point cloud data, impart some notion of connectivity, which is scale dependent, and then ask, well, what are the topological properties of these connections of those points as a function of that parametric scale. Okay, and the idea then is that if those topological properties persist for a long time, it's like as you vary, it's like that scale parameter, then you have some reasonable confidence that those topological properties, it's like are really sort of giving you some information about topological properties of the object you're really sampling the point cloud from. Okay, so we'll talk more about this. It's like as we go along. It's like, but for now, let me just stop here.